Hi there, Mr. Sutton here, bringing you the AB Calculus 6-9 Extra Practice Number 1 solutions on accumulation problems. On this problem, we have snow falling at a rate of this R of t function, and basically we want to know which expression tells us the amount of snow that falls from time 0 to time 5. So if I have the rate of snowfall and I want to find out how much fell, I just need the integral of this from 0 to 5. Well, that means I need to take the antiderivative since this is a no calculator problem. So antiderivative of this is going to be 2e to the negative 0.1t divided by the inner derivative of negative 0.1. So we're really, this is really negative 1/10 we're dividing by. So that means we're really multiplying by negative 10. So that's going to be negative 20 e to the negative 0.1t. And I'm evaluating that from 0 to 5. So let me take that negative 20 out of there. And inside, I'm just going to have e to the negative 0.1 times 5 minus e to the negative 0.1 times 0. And if I simplify this a little bit, inside I'm going to have e to the negative 0.5 minus, well, this is all just e to the 0, so minus 1. And it looks like I'm going to have to distribute that negative 20 after all to get one of my answer choices. So if I do that, I'm going to have, let's see here, a negative 20 e to the negative 0.5 plus 20. Or I could write it as 20 minus 20 e to the negative 0.5, which would match answer choice D. For this problem, we have a table here giving the level of a person's cholesterol at different times during a 10-week period. We want the average level over the 10-week period by using a trapezoidal approximation with the subintervals basically indicated by the table here. So for average value, you need to do 1 over the interval length. In this case, our interval length is from 0 to 10, so we have 1 over 10 minus 0 times the integral from 0 to 10 of, well, they didn't name the level function here, so I'm going to give it a name. I'm going to call this L of t, and I'll put a dt in there just for good measure. So this is going to be approximately equal to the following. So we've got a 1/10 on the outside. And now inside, I'm going to have a trapezoidal approximation of this integral. So let's see here, trapezoid area. I've got base 1 plus base 2 over 2 times height. So that's going to be 210 plus 200 over 2 times a height of 2 to go from 0 to 2. That's our first trapezoid. Next trapezoid is from 2 to 6. So that's a base of 200 plus a base of 190 divided by 2 multiplied by a height of 4. And then last one, we've got 190 plus 180 over 2 times another height of 4. And at this point, this is a no calculator question, but I'm going to have to simplify this in order to get one of these answer choices. So let's simplify the stuff inside first. Well, these 2's cancel for this first fraction, leaving me with just 410 for that. And then for this next one, let's see here, 4 divided by 2 is 2. Then we have 390 times 2, which is 780. And for this one, 4 over 2 is 2, times 370 is going to give us 740. And at this point, let me add these together and then divide by 10. So let's see here. Let me do the tens first here. We got a 10 plus an 80 plus a 40. That's a total of 130. So we have 130 plus 400. That's going to be, let's see here, let's do the hundreds. So we have a 130 for the tens. For the hundreds, we have 400 plus 700 plus 700. That's 1,800 plus 130, so that's 1,930. Divided by 10 is 193. Boom. Choice B. For this one, we have water flowing into a tank at the rate given by R of t, which they're not telling us exactly what it is algebraically, but they gave us a table of values for R of t. Now here's another important piece. This tank contains 15 gallons of water at time 0. We want to use a trapezoidal sum with 3 intervals to figure out approximately how many gallons of water in the tank at time 9. So you got to be careful here because, we are going to be taking an integral of the R of t function, but you can't forget about the initial 15 gallons of water that we start with. So we're going to have 15. So our water is going to equal 15 plus the integral from 0 to 9 of r of t dt. And this is all going to be approximately equal to the following. So we've got the 15 that we're starting with. Can't forget about that right away. And then we need a trapezoidal approximation using this table. So we're going to have 3 trapezoid areas, all of the form base 1 plus base 2 over 2 times the height. So for my first trapezoid, I've got bases of 9 plus 16 divided by 2 times a height of 4 from 0 to 4. For the next trapezoid, we have 6 plus 4 over 2 times a height of 3. And then we have 4 plus 3 over 2 times a height of 2. This is a no calculator problem, and we have to actually simplify this to get one of our answer choices. So let's keep going. 15 is still 15. That hasn't changed. This next one, we have 4 divided by 2 is 2, times this 15 is going to be 30. And then after that, let's see here. This is 6 plus 4 is 10, divided by 2 is 5, times 3 is 15. And then finally, these 2's are canceling, leaving us with just 4 plus 3, which is 7. Adding all this together, 15 is 30, plus another 30 is 60, plus 7 is going to give us 67. Well, that could have been worse, so that's going to be choice C. For this calculator-based free response question, we have an intersection in Thomasville, Oregon. Not sure if that's a real place, but hey, maybe. Cars are turning left at a rate given by this L of t function, and this is measured in cars per hour. This is happening over the interval from 0 to 18 hours, whatever time of day that is. And they were super nice. They actually gave us a graph of L of t. Sweet. We want to find for our first task the nearest whole number, the total number of cars turning left over the interval from 0 to 18. Well, we have the rate at which the number of cars, that we have the rate of cars coming through here, cars per hour. So if I want to find the total cars, I just need to integrate this rate over the interval from 0 to 18. So I just need integral from 0 to 18 of L of t dt. This is all I actually have to write because they already spelled out what L of t was up here. And now I'm just going to plug this in my calculator and get the answer. So here I am in my y equals in the calculator. In y1 right here, I've put my L of t function. And just be careful when you're entering this. There's a few things that could go wrong. So make sure that the only thing inside the radical is x. It's too easy to accidentally include other things that you didn't want to. Also, to do sine squared on the calculator, you have to do sine of whatever, close your parentheses, and then put the square outside the parentheses. And that basically does what this square does over here. So now quitting out of there, let me actually use the integral. So that's going to be math 9. And I'm going from 0 to 18. 18, there we go. Let me do alpha trace to pull up my y menu, and then there's y1. That's where I stored my L of t function. Let me arrow over and put a dx in there, and press enter. Now they wanted the nearest whole number here. We don't want a fraction of a car. So this ends up being 1,658 cars that are turning left. For this part of the problem, they're saying traffic engineers will consider turn restrictions when L of t is greater than or equal to 150 cars per hour. We want to find all t values for which this is true and then compute the average value of L over this time interval with units of measure. Okay, so we need to figure out basically when L of t equals 150, and then we'll do a little sign analysis just kind of looking at the graph here to help us figure out where this L of t is greater than or equal to 150. So back on my graphing calculator, let me go there. I'm back in my y equals where I already put the L of t function in as y1. Now for y2, I'm going to put in just a constant function of 150, and I'll basically see where these two things intersect, and that'll give me some endpoints for my intervals that I'm about to give them here. So let me see, what window should I use? Well, this function was valid between 0 and 18 hours, so let me use that for my window. So let me go to Window, 0 to 18, and zoom 0, zoom fit. All right, so this first thing that's being graphed, this is L of t, and it looks just like the graph that they gave us here, so this is a good sign. And there's y equals 150. So we see that there's only two places on this graph where we're intersecting. So this region in between those 2 points this is going to be all the time values where L of t is greater than or equal to 150. So let me find those two intersection points. I'll do second trace and then option 5 for intersect. Let me move my spider up here to the first intersection. There he goes. Enter, enter, enter. And then that's going to be about 12.4283. And I'm going to refer to that, so I'm doing L of t equals 150. I'm going to refer to that value as time A. That's a constant that I'm writing here. And I'm also going to store that on my calculator, so I'm storing it really on the paper and the calculator, so I don't have to keep writing it over and over again. So I quit out of my graph and I press the store button, and then alpha A, and now I can keep using that. All right, let's go back to the graph to get the other value. So here's my graph again, and let me do second trace option 5 again. And now I'm going to move my spider closer to the other intersection, right there. Enter, enter, enter. And that comes out to about 16.127, which I'm going to refer to hereafter as B, the constant B. And I'll store that on my calculator as well. So quit out of the graph. And now I'm going to do store to store the value that I just got. And we're doing alpha B. All right. So taking a look at the graph here, we see that between those two intersections, that's going to be the interval where L of t is greater than or equal to 150. So I'm going to say L of t is greater than or equal to 150 on the interval from, well, I've already given these numbers names, so I'm just going to say parentheses A comma B, and that'll do it. Now, we do still need to do one other thing on this. They want the average value of L over this interval. So average value, that's going to be 1 over the interval length. So that's going to be 1 over b minus a times the integral from a to b of whatever you're trying to average, which in this case is L of t. And we can just do this on the calculator now. So here is what I entered in my calculator off camera. I did my fancy fraction mode to do 1 over b minus a. And I've got the integral, math 9, from alpha a to alpha b. I did alpha trace to pull up my y menu, and I put y1 in there because that's where I stored L of t. We've got dx, and now we just have to press enter. And that gives us 199.426. And since this is the average value of L, and L is in cars per hour, this is also going to be in, cars per hour. There we go. For the last part of this problem, traffic engineers will install a signal if there's any 2-hour time interval during which the product of the total number of cars turning left, which we can find with an integral, and the total number of oncoming cars traveling straight through the intersection is greater than 200,000. Now, how do we figure out how many cars are coming straight? Well, they're telling us in every 2-hour interval, 500 oncoming cars travel straight through the intersection. So the only thing that's really changing is depending on which 2-hour interval you pick, there may be a different number of cars turning left, but the number coming through straight is always going to be 500. So we want to know if this intersection requires a traffic signal. Okay, so this is a little tricky because there's all these different possible 2-hour intervals that we have to look at. But in cases like this, it's always best to check out the worst case scenario. You know, at what time, if you just look at this graph, do you think you're most likely to need a traffic signal? Well, it's probably going to be the time where you have the most people, the highest rate of people turning left, about 15 hours in here. So we're just going to consider the max value of L of t, which we don't know exactly what it is. We probably could find it, but it's not worth it. Let's just consider a value that's close to the max, which is going to be whatever value we get at time 15. So let me consider an interval around time 15. How about the interval from, say, 14 to 16? That's going to have a lot of people turning left. And if that's not good enough, then maybe we can be a little more precise about where the max value occurs. But let's start with the interval from 14 to 16. That's pretty easy. So the integral then of L of t from 14 to 16, let's do that on the calculator. So here we go. Integral, math 9, 14 to 16. Now remember I stored L of t as y1, and we put a dx in there, press enter, and that comes out to roughly 412. So we'll just round it off to the nearest car here. So we have 412 cars that are turning left during that time interval. Now they said that we're going to need a traffic signal if the product of this number, the number of cars turning left, and the number of oncoming straight going cars, is greater than 200,000. So we're going to multiply 412 by 500. And if we do that on the calculator now, 412 times 500, that comes out to 206,000. 206,000 is greater than that threshold of 200,000. So that tells us that we definitely are going to need a traffic signal at this intersection. For this calculator-based free response problem, number of gallons, which we're calling P of t, of a pollutant in a lake, is changing at the rate P prime of t equals all this crazy stuff, and that's in gallons per day. So there's 50 gallons at time 0, and the lake is considered safe when there's 50 gallons or less of pollutant. Yeah, apparently 40 gallons is safe. Okay. So anyway, is the amount of pollutant increasing at time 9? That's our first task. Why or why not? So to figure out if our pollutant is increasing or decreasing, we look to P prime, which tells us the rate at which the pollutant is changing. If P prime is positive, the pollutant is increasing. If it's negative, pollutant is decreasing. So what is P prime of 9? Well, let's just do that on the calculator because they've already defined P prime for us. So here we go on the calculator. I feel like I'm going to have to use P prime a few times on this free response problem. So I've entered it in my y equals under y1. And now let me just quit out of there. And I'm just going to do alpha trace to pull up my y menu. And let's just do y1 and open a parentheses and plug 9 into that. And that comes out to about negative 0.646. And that's going to be in gallons per day if you wanted to write the units. I don't think you have to here, though. So the fact that this is a negative value, that it's less than 0, this indicates that the amount of pollutant is actually decreasing at time 9. For this part of the problem, they want to know for what value of t will the number of gallons of pollutant be at its minimum and justify our answer. So this is a little bit tricky because often when they ask for a minimum or a maximum, it's on a closed interval, but they did not give us a closed interval here. They did not say that this function was valid for 0 to some specific day. This is just valid apparently for all of time, often to infinity. So in that situation, we can't use the candidates test because we do not have endpoints. So that means we're basically going to have to show, if we're looking for a minimum, we're going to have to show that this is P prime is less than 0 until some day, and then greater than 0 after that particular time. All right, so let's figure out at least when P prime of t equals 0. So to do this, let me go to the grapher. So just to show you again, I've entered P prime of t in my y equals under y1, and I really have no idea where this is going to cross the x-axis. I mean, I can try doing zoom 6, just a standard zoom, and it's going up and up and up, and I'm not sure where it's going to cross or even if it's going to cross. So if you're not really sure about this, one thing you can do is check out the table. So let me just do table set here and see what the settings are. So I'm starting at 0 and going by 1s. Now let me just go to table and see what my P prime is doing as I go. So we see that as we get lower and lower here, which means higher and higher input values, our P prime value over here is getting closer and closer to 0. Will it ever pass 0? It looks like it's going to, and it does, somewhere between 30 and 31, but we kind of need the exact value here. So let me go to, let me see here, let me go to Window, and I'm going to make my, my x values go from, let's say, 0 to, let's do 32. 30, let's do 40. Let's do 40. That'll give us a nice window. And let me do now zoom 0. And this should give us the perfect window we need to find that intersection point. All right, so it happens somewhere around here. Let me do second trace, option 2 for zeros. And we know that this happens between 30 and 31. So let me enter to the left. Press enter again a little bit to the right, enter one more time. So that happens at 30.174 about. And we're kind of wondering, are there any other places where this thing crosses the x-axis? Well, if you think about what this function is doing, as t gets really, really big, this basically becomes e to the, that's going to be e to the negative infinity, which means 1 over e to the infinity, which is just going to go to 0, and it's going to zero out this 3. So we're not going to become negative again. If anything, this is just getting closer and closer to 1. So we don't have to worry about our function coming back down, as it were, and crossing the x-axis again. All right, so here's what this shows us. And by the way, I'm going to store this as a, just so I have it for later. So p prime equals 0 at t equals a days. And we see here that p prime of t is less than 0 on the interval from 0 to a. And p prime of t is greater than 0 on the interval from, t greater than a, often to infinity. So this tells us that the minimum value has to occur at time a, which is to say 30.174 days. On this part of the problem, they're asking if the lake is safe when the number of gallons of pollutant is at its minimum, and justify the answer. Well, we found the time in part B where we were at the minimum. Going back to my calculator, that was this 30.174 time, which I'm actually going to go and store as the value a. So let me press store and alpha a. There we go. I already labeled it as a in part B, but now I'm going to store it as a on my calculator as well. So since that's when our pollutant's at its minimum, to figure out how many gallons of pollutant we have at that time, we have to take the 50 gallons that we're starting with, and we have to add to that the integral from 0 to time a, which is roughly 30, of our p prime of t function. So 50 is my starting gallons. This integral here is the change in gallons from time 0 to time a. And let's do that on the calculator. So here's what this looks like if you plug this in. We have 50 plus, I did math 9 to get integral. We have 0 to alpha a, which was this number up here. y1 is where I stored my p prime of t, and I put an x always there for dx. Press enter, and that comes out to roughly how many gallons of pollutant? About 35.104 if we round that off. So how many gallons is considered safe? Well, reading the problem, they said it's safe if we have 40 gallons or less. Since this is less than 40, that implies that the lake is safe. Not too many gallons of pollutant. For this last part of the problem, an investigator uses the tangent line approximation to p of t at t equals 0 as a model for the amount of pollutant in the lake. We want to know at what time does this model predict the lake becomes safe. So in general, I'm going to use my, my tangent line approximation formula. So we have basically L of x equals f of a plus f prime of a times x minus a. So f of a, in this case, a is going to be 0. That's the launching off point for your tangent line, which they said was time 0. So this f of a is really f of 0, which is the amount of pollutant in the lake at time 0. That's 50 gallons, so we've got 50 there. So I'm going to write L of x equals 50. I'll write L of t because it's time here for the input. And this is going to be f prime of 0 right here, which is to say p prime of 0. So up here, that's what happens if you plug 0 in for t. Now, we could very easily do this on the calculator, but we could do it without a calculator too. If I plug in 0 for t, this is just e to the 0, which is just 1. So multiply that by 3 and you just have 3. So this is really 1 minus 3, which is just negative 2. Nice. And then we have essentially, this is going to be t minus 0 in here. So this is our tangent line approximation formula. We want to know at what time the lake becomes safe. So at what time does this equal 40 gallons? So we're going to set this whole thing equal to 40. And if I set this equal to 40, well, subtract 50, we've got negative 10. Divide by negative 2, that gives us t equals 5. So at 5 days, apparently this lake is safe to swim in.